Okay, in previous lecture, we learned how to train the classification network. Okay, so first we learned about the binary cross entropy laws and also the logistic regression. And you also agreed that these binary cross entropy laws can achieve the binary classification task. Okay, and in PyTorch you can implement logistic regressor in this way. And logistic regression algorithm that is actually performing the binary classification task. Okay. And also we learned about the softmax that can help us to achieve the multi-class classification. Okay. So at the last layer, the deep architecture's responses will not be bounded, but we need some of the probability vector that have two characteristics. First, each element, each probability have to be larger than 0, and their sum have to be 1. Okay. To meet this, we need apply the softmax layer. And also, we learned about cross entropy laws that can help us to implement the classification network. Okay. So let's say the ground truths are one hot encoded vector, and using these cross entropy laws, your prediction Q could be close to the one hot encoded ground truth. Okay. And yeah, in the PyTorch, you can implement that using one line of code. Okay, you can just make the cross entropy laws by calling this function. But when using that, there could be some confusion because the dimension of input and output is different when using the cross entropy laws. The PyTorch can implement that as the same dimensional vectors for this input and ground truth. But for simplicity, actually, they made this target, which is the ground truth, as this integer array rather than explicitly making them into one hot encoded array. So be careful when using these cross entropy laws. And also we learned about the early stage CNN architecture, whose name is LUNET. Okay, and the input size is very small and having the grayscale image. And at the last layer, it will output 10-dimensional vector, which may denote the probability for each digit. Okay, because there are 10 digits, we have to estimate 10-dimensional vector. Okay, and we will implement that for 10 classification task. Okay, so I already explained this kind of hyperparameters before, and I also explained how to define this LUNET architecture. Okay, so roughly it is composed of two kinds of layers, which are the convolutional layers that extract some features using the 2D convolutional layer. And after that, we flatten the signal to one-dimensional signal, and then we apply fully connected layer that is composed of linear operation and also having some non-linearity in between linear layers. Okay, that is the architecture of the LUNET. And then actually I missed one thing throughout explaining this kind of code. I actually missed one thing. I already explained that these 5 lines of code is very important and can be repeatedly used for training any kind of network. Okay, but I omitted how to load this X and Y data. Okay, so you need this X and Y data to train the networks, but I just denote them as X and Y variable, but actually in this code, there is no code for loading them. So I will actually explain that from now on. So there are actually two ways to load the data in PyTorch. Maybe three ways, but I mean, you can directly implement how to load X and Y data by yourself. But I recommend you to use either of these two ways that I will explain now. So the other way is using, it is the way we can load the data in the PyTorch is actually consists of two things. So we have to first define the dataset variable, and then we will use that in the data loader. Actually, the way to load the data in PyTorch is composed of these two things. First, we have to define dataset itself, and we will input it to this data loader. Okay, and dataset actually it returns. I will explain this first. So here we can actually define our own data set. Okay, so actually we will define it as the class. Again, similar to how we define the network, we will also define new class for the data set. Okay, and actually there are three methods in the dataset class. Okay, the first one is the constructor, and the second is the length method, which denote the number of samples in your dataset. Okay, so it will return the length of the entire data. And the third one is very important, and you have to return actual data in this method. Okay, so I mean, the constructor actually these two things have to be, either of these two have to be implemented. First, the data itself could be there in the init function, the constructor, because it is once executed when the class is initialized. So dataset itself is initialized in this constructor, or I mean, in our case, we are dealing with the images or videos. So the path to image or video or any other files need to be defined in this constructor. Okay. So for example, I mean, if your data set is small in scale, then you can, for example, here we define 5 samples. Okay. This X data is meaning the raw data, okay, the input data, and Y means their corresponding labels. Okay. So you can define every data in your constructor function if the data scale is small. Okay, are you agree with this, right? But if your data is large in scale, then you can also put some of the paths to your raw data, okay, in the constructor. Okay, and also in the length method, you have to define how to, let users know about the number of data sets. So if you call this, then you can also know the number of data set in your raw data. So they implement that as like this, but using other data, like, or if you use the path, then you have to define this maybe differently. Okay. Anyways, the second method have to return the number of samples. And the last one, you have to implement how you will return the raw data. So here, because we already have already defined our X and Y data in our constructor, so we can directly access this data here, and you have this index variable that point out, the order of the data. So you will load that data from this array, okay? defined in the constructor and typecast it to float PyTorch variable and save it here x and y and will return that. So this get item method is actually implementing how you will return your own data for each sample. Okay. So in this data set class, you have to implement how one sample is loaded. Okay. And also this could be very simple because your data is small in scale and you directly implement all the data inside the constructor. You can just access their index and return it. But if your data is large and you only can write the path to the actual data, then the thing you have to do is you have to actually read this image or video or other files in your getItem function. You have to read that explicitly and process that and return it, have to return it, okay? And and later, you will define the data loader, okay? So this is how you will define your data set, which specify how you will load each sample. And then you will, input this data set instance to the data loader. And that data loader actually help you to load the data in this way. So the thing you will do next time is you will write down this for loop, and this is the data loader instance you will define later. And from this data loader, you can actually load the data in this format. You define exactly the format you defined is in this get item method. You can automatically load all the data sequentially. Okay. So this is how it works. So, but the other way is in the PyTorch, there's already defined this dataset instance for famous datasets, such as MNIST. MNIST or CIFAR 10, CIFAR 100, or ImageNet, they are very famous dataset, and users frequently use that implementing algorithms. So the PyTorch already implement those dataset in the built-in function. So instead of implementing this kind of dataset function by yourself, you can just call this kind of dataset MNIST function to make this dataset instance. And here, the thing you have to specify is whether you will use the train split or test split or some of the options for applying transformation function. And anyways, in this kind of function, the PyTorch also provide you some convenient way to load the data, okay? And anyways, after that, after defining the dataset instance, the thing you have to do is you have to define your data loader class, okay? Data loader is already defined, and the thing you have to do is just making some new instance using the data loader class, okay? But when initializing this data loader instance, the thing you have to do is inputting this data set instance you just defined here into here. And for the test loader, you have to input the data set, the test data set you just made into this data set argument, okay? And also you can also define some of the batch size, and there are some other options for shuffling things, okay? Shuffling means, you can, if you make this shuffle flag as true, then your data set order is shuffled, okay? they will be in the random order. Actually, for the training data set, the shuffling could be good for, preventing some overfitting phenomenon, maybe. So for the training data, you will do this shuffling, but for the testing data, we normally do not do any shuffling, because for the testing data, we normally traverse all the testing data and measure the accuracy on their I have to say performance. Okay, but so the order of traverse is not important when loading the test data. So, but during the training, supply training data set in the random order can help the training stage, giving some randomness to prevent the overfitting. So we normally do shuffling. And also this batch size means the number of image units that is simultaneously processed. Okay. Anyways, now after subsequently, we use this data loader instance in our for loop. Okay, so this data loader instance is made by inputting actual data set instance, which have the information for our data format. Okay, and in the for loop, you can load using this data loader, load the data in the format you described here. Okay. So this is how you can load the data easily in the PyTorch. Okay. The frequently used data sets, this kind of data set class is already implemented in this link, so you can search for that. But if you want to use your own data set, then you have to make this kind of data set class by yourself, and then you can use the data loader class. Okay, are you guys following this? Okay. And the other thing we have to also have to change our scheme might be we now till now we learned about the gradient descent, but we will also change it to stochastic gradient descent. Okay, so you already see that our code is using the SGD as the optimizer. So you may see here, actually our optimizer was SGD. So this means stochastic gradient descent. Okay. But we can use that because their actual formula is not different. So the stochastic gradient descent, that means this kind of thing. Okay, this formula is same between this SGD and GD. They are sharing the same formula, but the only difference is in the gradient descent, we calculate this DL dissector for all the data, okay? And then update this only once after seeing all the data, okay? So the formula is same, but how much you will execute this formula is actually differs. So, but stochastic gradient descent, you calculate this gradient many times after seeing partial data. Okay, so DL dissector is calculated many times compared to the gradient descent in stochastic gradient descent. Okay, and of course, because you are seeing the partial data, it takes small amount of time. Okay, and you execute this entire formula multiple times while seeing the all data. Okay, gradient descent, it just once, calculate DL dissector and also calculate this one time after seeing all the data. The stochastic gradient descent, it calculates this after seeing partial data and also execute this update multiple times while when seeing all the data. Okay, that's the only difference. So gradient descent, And if your training data is this, then gradient descent works like this. After seeing full data, it once update your parameter. Okay, but SGD, your training data is divided into mini batch, and you update your parameter multiple times. That's the difference between SGD and GD. But you may think that GD might be better and SGD might be not optimal. But you have to think about this. The train data and test data is different, okay? So we are actually training our parameter sector using this training data, but we are evaluating our parameter. We have to test it on the test data, okay? So, the accuracy, the performance of the model is not decided by the training data, but by the testing data. So it is meaningless. In the aspect of the training data, the model is actually optimal, right? But that is not optimal, may not be optimal for the testing data. But the important thing is having good model for the testing data, okay? So it is meaningless to secure the model that is actually optimal for the training data. Actually, that is overfitting phenomenon, okay? So if one model is overly fitted to the training data, that is called as the overfitting phenomenon, and it would not be operate well on other data set, including our testing data. So this is not desirable situation. So gradient descent that is optimal in the aspect of the training data, but that is not actually good situation. That is actually meaning the overfitting. Okay, so to avoid that, actually stochastic gradient descent is used. Okay, in the aspect of the training data that could be regarded as non-optimal update, but this kind of randomness can help us to generalize to the test data. Okay, so you can think this space as the parameter sector. This figure, this is the parameter space. Okay, and gradient descent is doing this kind of thing, using the training data by seeing all the data once and go one optimal steps in the aspect of the training data. And the SGD, they are because they are seeing the partial training data and update multiple times using that incomplete gradient. But anyways, in practice, because our aim is to make the model generalized to the test data, so in practice, this SGD works better than the gradient descent. Okay, are you guys understanding this? 다 이해하고 있나요? So, and our implementation also will be slightly changed. So if you think about how we implement this linear regressor, for example, here, logistic regressor, we assume that this x and y, this variable is having all the data we will use. Okay, so epoch means epoch is roughly same as the iteration, right? But epoch is normally meaning that seeing all data once. Okay. If your model see all the training data once, that actually means one epoch. Okay. Okay. So this code works for seeing one time x and y. Okay. So actually we are assuming that this X and Y is having all of our data. Okay? So this is actually the implementation of gradient descent. Okay? So when doing the forwarding and calculating the loss, when calling loss step backward, DLD sector would be calculated for whole data you are having, and then update your model once after seeing all the data, and then do another update uh, at, at the next epoch. Okay, so actually this is the implementation of gradient descent, and this is actually easy to implement when your data is small in scale. I mean, this X and Y have to contain all the data you have, but the data set is big and the memory is not available, then you cannot contain all the data in this X and Y variable. So this code will not work, okay? So, but I mean, in implementing the deep architectures, there have to be a lot of data set, okay? So this is actually the implementation of the stochastic gradient descent. Okay, so this is the for loop you already seen. Okay, so this is actually the code for loading X and Y from your data loader. And when loading this data loader, I mean the data from the data loader, it is loaded in the batch size with the batch size. Okay, so here you already specify the batch size. Okay, the batch size means the number of images simultaneously processed. Okay, so I mean here actually the X and Y, those are loaded simultaneously in, I mean, but maybe which data we use, okay. Batch size in our case is 32. So here, X and Y, that is 32 samples are loaded together, okay? But our data, actual data is larger than this. These 32 samples might be the partial data we have, okay? And then we do forward and calculate the loss, okay? And this is some visualization things, okay? And then apply loss step backward to calculate DLD sector using these partial samples, okay? And then update our model once, okay? Applying the gradient descent. And actually, because this works for each partial data having this number of samples, this is actually the implementation of the stochastic gradient descent. Okay, I agree with this. Okay, so I mean, because your data is big, you cannot contain all the data in this X and Y variable. And also in practice, I mean, that's the reason why you have to think about this kind of partial update, okay? But in practice, this partial update is better than the gradient descent, which updates after seeing all the data. I mean, because of the reason that I mentioned earlier, okay? So actually, this is the training code I mean, this is the training code for one epoch. This train function is training your model for one epoch. One epoch means for seeing all the data once, you have to implement your training code in this way. Okay, so this code will loop through the data loader to see all the data using this 32 sample unit. Okay, and for partial data, you will call the same training code we learned. Okay, and forward and load step backward and update That code is called for each batch. And this is, loop through all the data and then finish. Okay? This is one epoch training code. And this is the one epoch test code. Okay? Test means you will apply only the forward step using your model. Okay? So you also have to load your X and Y data from the test data loader. Okay? And you will apply the forward step, but you have to figure out that there's no backward step and there's no parameter update code. I mean, these two are omitted in this test code, okay? The thing you have to do is just collect how many samples are correct and how many samples are loaded. And if you divide that, the correct samples by the total number of samples, then that could be the accuracy for that epoch. Okay. Anyways, this is the testing code for one epoch. Okay. Are you guys following this? Easy, maybe. And this training loop is the training code for entire epoch. Normally, we maybe use 100 iteration to maybe 10,000 maybe epochs or more epochs. Okay. Anyways, this is the code for entire epochs. So you will reuse this train and test function you redefine for one epoch. Okay. And this is the loop for 100 to 1,000. 10,000 epochs, okay? And inside that, the thing you will do is this two. Once train your model for one epoch and do testing for that model, okay? Then this is the visualization for obtained model, okay? You have to see their loss and their accuracy, okay? And you have to iterate it through your epochs, predefined epochs. Okay. So for each epoch, you have to do one training and then do testing to evaluate your model's performance. And this is also interesting code. This is also interesting code. If your code do not involve any backward function, then in the PyTorch, when doing the forward function, when calling the forward function inside the PyTorch, some of the graphs are constructed automatically to potentially do backward things. Okay, when I already told this, inside the PyTorch, this type of graphs are made to do back propagation. While doing the forward function, this type of graphs are constructed to achieve the backward. But if you only do testing, which means if you only want to do the forwarding of the model, then you don't have to construct this kind of graph. Okay. Then in that case, you can specify this to the PyTorch, and inside this code, if you call the test code, your test code, which does not require any backward function, then this kind of graphs will not be constructed, and the entire code could be more efficient. So that's why we have this kind of code. Okay. Anyways, this is the implementation of the training code for entire loop. And also in the top level, you have to make an instance using your class, LUNET class you defined previously, which is here, okay? So this kind of network have to be initialized here, okay? Model initialization. And also you have to define your SGD optimizer, and also you have to define your own cross-entropy loss. And then you have to run your training loop code, okay? And I mean, after looping, this model will be the final best model. Okay? And while calling this executing this code, maybe you can try, calling this whole entire code in the Colab, and you will see this type of information, okay? And that is actually outputted from here, okay? For each epoch, you will print out each training loss, test loss, and accuracies, okay? And they are actually seen like this. And I mean, for each epoch, you will see the training loss, test loss, accuracy, training accuracy, and test accuracy. And you can see that their loss is gradually reduced and the accuracy is gradually increased. Okay, but the thing is, I mean, when you first execute the code, then normally by default you will use only the CPU, and I mean, executing this code might take a lot of time, right? For maybe 15 epochs, it will take a few minutes. This is quite slow. So, sorry, in the Colab, you can set the GPUs, okay? To execute the code, you can also use the GPUs. So if you type this kind of code in your Colab environment, then by default, it will return the false. So this torch.CUDA is available. This is the flag which indicates that in your Colab environment, the GPU environment is ready to use or not. Okay. So if this is returning the false, then it means your environment is not ready for the GPU. Okay. So in the menu, you have to select this kind of change runtime type. And also you have to select GPU type here, okay? And after doing this, okay, in your menu of the Colab, you have to select this. And then you may see that this flag will be changed to the true, okay, true status. Okay? And now it is indicating that your environment is ready to use the GPU. Okay, so you have to set this to use the GPU. And also after that, but in your local machine, you also have to buy some GPU and install it properly to see. You have to see this torch.CUDA that is available flag is changed to true before using the GPU. Okay. And then in your code as well, you have to also make a few changes. The first thing is you have to copy data to GPU, okay? And also you have to copy your model, deep model to GPU, okay? You have to do this kind of two things, okay? And to copy your data to your GPU, the grammar in Python is like this. X and Y, this is the data loaded from the data loader. And dot to and specify the GPU name, okay? This is the grammar for copying your data to the GPUs, okay? Same for the test code, okay? And yeah, so this device, the GPU device name, it will be implemented in the top module. So you have to transmit the information to the downstream functions. And here is the code for defining the device. Okay, your device is having the CUDA if the GPU is available. Okay, but unless your GPU is available, then it will use the CPU flag. Okay, this is meaning CPU mode, and this is meaning the GPU mode. Okay, and also you have to copy your model to the GPU, and this is the grammar for that. This LUNET is the class for initializing your model. And by doing this, your model will be copied to the GPU. And you will transmit the device information to the downstream functions. Okay. So this is a few changes when you want to use the GPUs in your code. Okay. And now the result would be same, but the execution time might be much faster. Okay. So that's the thing you can achieve when using the GPUs. Okay. So this is the thing I prepared for implementing the CNNs, basic CNNs, using the PyTorch. Okay, and from now on, I will also want to share some of the recent CNN architectures. Okay, to you. So I mean, this LUNET, as I mentioned, is very early models, which is proposed in 1980s. But as I told you in the first class, I mean, this time, previously, I mean, in the year of 2011, the best model that performs in ImageNet challenge, that wins the ImageNet challenge, was the shallow learning algorithm that is composed of, that is actually using the SVM, which is the shallow learning method. But in the year of 2012, there's a huge gap between the previous year's best algorithm, almost 10%. Okay. And this is actually the first successful CNN architecture whose name is AlexNet. Okay, I mean, the reason why this is called as the AlexNet is the author of this paper is Alex Krzyzewski. So this is following his name, actually, this network, AlexNet. And afterwards, very famous deep architectures are proposed afterwards. And this is the VGG in the year of 2014. The VGG network was proposed from the Oxford. And this is in the same year, the Google LUNET was also proposed from the Google. Okay. And after that, in the year of 2015, the ResNet is proposed by Kai-Ming He from the Microsoft. So today I will show you how their design policies, philosophies are okay, coming from. Okay, and also I will show some of the code that can implement this type of CNNs. Okay, so first is the AlexNet. So I mean, the AlexNet is first successful CNN architecture after the LUNET. Okay, LUNET was successful in small-scale data, but the problem was because of the overfitting phenomenon, it is not generalizable to a large-scale data set. And at the 1980s, there's not much resources. For example, there are not much data, I mean, the storage devices that can save large-scale data. At the same time, there was not much good GPUs. Okay, but this AlexNet, one of the innovations in AlexNet is they are first proposed to use the multi-GPUs when training the data. Okay, and also they are using ImageNet dataset, which is large in scale. Okay, so that actually is different from the situation of the LUNET. Okay, and also they also involve some of the few more schemes called as ReLU and dropout and data augmentation. So most of them are related to how to say, I mean, relieving some of the weaknesses of the LUNET architecture. Previously, you may remember that tangent hyperbolic functions are used when implementing the LUNET. Okay, but one good thing in LUNET, not LUNET, ReLU function is, I mean, this is tangent hyperbolic function. Okay, this is 1 minus 1 line. Okay, so I mean, getting some how to say dy dx, which means given one layer, there are input x and there will be output y. Okay, so we have to actually define this type of gradient. We have to calculate this gradient. Okay, but I mean when the x signal is in this range, okay, then gradient means this type of slope. Okay, when relatively input values they are having the small scale, there are some meaningful slope. Okay, which means these gradient values are meaningful. But if I mean their ranges are becoming larger or becoming less, then you can see the gradient of this tangent hyperbolic that actually becoming close to zero. Okay, so actually this kind of characteristic is actually hindering the proper training of the deep architecture. So, but I mean, ReLU function, if you see the ReLU function, uh, I mean, this kind of gradient is very clear. Okay, they always have 1 and 0. I mean, x is less than 0, they will have 0, but x is larger than 0, then they have the clear gradient. So, I mean, that's the reason why ReLU is helpful for this faster convergence. Okay, and also. This dropout and data augmentation, those are two schemes which made these AlexNet works. Okay, data augmentation, maybe we will have some more materials for this, but I also think that most of you are already familiar with this data augmentation. So data augmentation is doing this kind of thing. Given one image, let's say it have a human class inside. Even though we flip left to right of this image, maybe if they are in this side, if human is in this side, by flipping left to right, the human would be in this side, but their class would be human. Okay, in both image, their semantic class would be human. Okay, but we can input this both image into the deep architecture and use them as the new data. Okay, we can use this type of new images as the new data, and that is actually make us to use double data. Okay, so by using this kind of simple image processing, apply this kind of simple image processing algorithm, we can actually multiply our data. Okay, not merely this kind of flipping, but we can also change their color distribution, or also we can make them in the grayscale image. Anyways, by slightly changing the characteristic of the images, we can multiply the data itself. Okay, that's the data augmentation. And also the dropout is, maybe I will explain that later again. Dropout is the scheme that can also give some randomness during the training. So giving some randomness during the training is helpful for preventing the overfitting. Okay, so I mean training means finding sector from training data. Okay, but finding sector that overly fitted to the training data is not good for testing data. Okay, so because of that, while tuning our model parameters to training data, giving some randomness is helpful in general. So this dropout, you can think that you can give some randomness for when training your model. So using this type of schemes and using large scale data with the multi-GPUs, this AlexNet indeed made the SOTA performance in ImageNet challenge by large gap. So using deep learning, this was the first successful CNN architecture. And this is the code for implementing the AlexNet. Okay. So most of the layers are very similar to the LUNet architecture we saw in previous slide. Okay. But the difference is we are using ReLU activation rather than the tangent hyperbolic. And also we are using max pooling instead of the average pooling. Okay. Okay, and also you can see in the fully connected layer, there's dropout layers newly introduced. Okay, this dropout is giving some randomness to the model only during the training. So dropout is activated only during the training, but at the testing, this is just multiplying one. Okay, so I mean, also in between the linear layer, there's a ReLU. Okay, so this is the difference in the AlexNet, and you can also feel that compared to the LUNet, the AlexNet have more layers, and it has actually the 8 layers. Okay, so 8 layers. Okay. And subsequently, the researchers are gradually increasing the number of layers. Okay? You will feel that later. And this is the forward function. Okay? So this is the implementation of the AlexNet. And also, this AlexNet is proposed in the year of 2012. And year of 2014, there were Bridge network is proposed from the Oxford University. And their philosophy is actually making deep architectures have more layers, okay? Making deep architectures deeper, that's the philosophy. And the conclusion is, if you make the deep architecture deeper, they could take more resources, but their performance becoming better. Okay. So in VGG, they make some deep architectures that have 11 to 19 layers. Okay. So this is the AlexNet having 8 layers. Okay. 5 convolutional layers and having 3 FC layers. That's the AlexNet. But here you can feel that there are a few more layers. And actually there are 4 to 5 versions of the VGG network. So VGG 11, 16, VGG 19. The number is indicating the number of layers. Actually, and also they stack 3 by 3 convolutional layers to constitute this VGG network. Okay, so they investigate the relationship between depth of the network and the overall accuracy. Okay, so you can see that in their constructor, they first define several blocks. Okay, that are mostly consist of the 2D convolutional operation, ReLU and max pooling. Okay, they define this type of intermediate blocks first. Okay. And also here they define totally 5 blocks, but mostly they are having their 2D convolution layers are having these dimensional filters inside. Okay, they are saying that these 3 by 3 filters are effective to make the deep architectures deeper. So that's why they are using this 3 by 3 filter. Okay. And then what they do is, actually they also have to define the FC layer here. And what they do is they apply the blocks they define sequentially and flattening it and apply the FC layer afterwards. Okay, that's the implementation of the VGG network. You feel that here VGG network, there are more layers, more convolutional layers. Okay. And that actually lead to better accuracy. Okay. And the next is the Google LUNET, and this is also proposed in the same year. And this is, proposed by some researchers in the Google, and they named this as the Google LUNET. By expressing some respect to the Yan Likun, who proposed this LUNET architecture, which is proposed in 1980s, early 1980s. Okay. Anyways, this is the naming things. And also, but this Google LUNET is slightly different from standard, how to say, CNN architectures, okay? In the sense that they are using these inception layers as the basic block. Okay, so previously we just sequentially apply convolutional and nonlinears and max pooling, some of the pooling layers sequentially. But Google LUNET, they are doing something different. And actually, this is the inception module, which is the basic block for this entire Google LUNET. And what they do is, this is the previous layers output, and you will apply this type of 4 operations simultaneously and concatenate them to make the output for this layer. And this is the inception layer. So, 1x1 convolution, 3x3 convolution, 5x5 convolution, and 3x3 max pooling, you will apply to previous layers output, and then you will concatenate their responses. Okay, and using these inception blocks multiple times, you will constitute the overall Google LUNET architecture. And the different characteristic is there is no X layer in this Google LUNET. But with this new basic block and without X layer, they are a winner in 2014, okay, in the ImageNet challenge. And I will show you how we can define the inception module. Okay, so this is the definition of the inception module first. And you have to define 1x1 convolution. This is the 1x1 convolution, 3x3 convolution, 5x5 convolution, and this is the 3x3 pooling. Okay, you have to define these layers and then apply them simultaneously, and then concatenate all the 4 responses and return it. Okay, this is the definition of the inception module. Okay, this is very easy to implement, right? This is the implementation of this inception module. Okay, and then you will use that inception module inside your entire Google LUNET architecture. Okay, actually 9 times. And the first layers, they are composed of the convolution, max pooling, convolution, max pooling. But second layer, they are composed of inception modules and max pooling. And third block have multiple inception modules and max pooling. And last layer also have multiple inception module and average pooling. And this is the 4th function, layer 1, 2, 3, 4, 5 sequentially, and doing flattering. And F's layer, it has 1 linear layer at the last layer to map it to the probability, okay? But no F's layer means they don't have multiple stacked layers, MAPs, at the last, okay? Anyways, they require 1 linear layer at the last, okay? And this is actually the definition of the LUNET architecture. And this is the last ResNet, okay? So, so far we learned that we can define deep architecture, okay? Sorry. ResNet is actually very important. So far we learned AlexNet and Bridge network and Google LUNET. So AlexNet have the 8 layer, and this have a 19 layer. Google LUNet have 22 layer. But ResNet, you can see they have maximally 152 layers. Okay. And you can also remember that, you have to also remember that this ResNet outperforms the human performance in ImageNet challenge, okay, in the year of 2015. Okay, so you may learn that from the VGG network, they experimentally showed that if we stack more layers, then the performance of the deep architectures will be increased, okay, becoming better. But the thing is, this kind of strange things occurred while stacking more layers. So, I mean, this is indicating the training error, and this is indicating the training iterations. And if you are having the 20-layered architecture, the training error, I mean, they are becoming less, okay? Error should be less, okay? So actually, if you have, let's say you have 8-layer architecture, their training error might be like this. But if you stack more and more layers, then their training error and also the testing error will be reduced, okay? This is, let's say, 8-layer. So, I mean, in the scale of this 20-layer, if you stack more layers, then their performance is becoming better. But if you stack more than 20 layers, and eventually if it has the 56 layer, you will observe that their accuracy is becoming less, okay? So this is a very strange phenomenon the deep researchers, deep learning researchers occurred, okay? So, I mean, 20 or some layers, I mean, that's why for the VGG network, it only have this number of their depth was limited by 20, okay? This is some strange phenomenon the deep learning researchers are meeting in this period. But one hypothesis was this. Okay, I will show you the exact reason why this is not performing actually. So let's say the deep architectures are having multiple layers, okay? And this is the initial input X, and this is the final output Y. And also we will calculate the final loss, okay? And each layer have its own parameters, okay? Like this. So we have to calculate all of this gradient, right? And then use the gradient descent to update each parameter, right? That is what we learned now. But the thing is, when calculating, for example, DLD sector 1, okay, DLD sector 1, which is the differentiation of the final loss respect to the first layer's parameter, then via the chain rule, we have to calculate this. Maybe, let's say this is Y1, the intermediate outputs are defined like this. Then this would be defined, how to say, in this way. How to define it? Maybe by the chain rule, DLD sector 1 will be calculated by multiplying several layers gradient. I agree with this, okay? But the problem is these values, the gradient values, are normally in small in scale, and they are normally less than 1. So if you multiply some floating values, which is less than 1, for example, if you multiply 0.5 20 times, it would getting close to 0, okay? And if the precision of the computer cannot represent the small number, which is very small in scale, maybe, let's say 0.5 is 20 power might be this, then if the computer cannot properly represent this small number, then it simply will regard it as 0, okay? Which means the new parameter will not be updated because that gradient value simply goes to 0, okay? Are you guys understanding this? So this is actually the phenomenon called as vanishing gradient. There are multiple ways why gradient vanishes, but this time the reason is because of the precision of the computer. If you take multiple layers, their multiplication of gradient becoming very small, and they are eventually goes to simply regarded as 0. And because of that, the parameters are not further updated, okay? So when stacking more and more layers, this kind of phenomenon occurred, okay? So to prevent this, a very simple solution was proposed in ResNet, okay? So I will explain that and finish this course, this lecture today. So this is the plain layers. This is the input, convolutional layer, and nonlinear layer, and convolution layer, and output, okay? This is the stacking of the normal CNN architecture. So how to say, we can represent the output h of x is fx. Okay, we can regard these two convolution as f function. Okay, and then this is h of x is equal to fx. Okay, but if we have this kind of route, that is just I mean the adding the same signal to x to the subsequent layer, then now the h of x becomes like this. Okay. I mean, this is very simple, but this gives us very good characteristic. So previously, when you try to calculate the differentiation of this if f function have multiple layers, maybe larger than 20 layers, then it simply goes to 0 because of the precision issue. But now you will see that if you if you apply differentiation of x to here, then that will become like this, okay? And this could be very small, but I mean, because of this one, the gradient is having some value instead of 0, right? Okay. So thanks to this one, I mean, the scale of the gradient is becoming more stable than before. And even though you stack more and more layers, this kind of parameter update can be occurred, okay? So thanks to this good characteristic, having this kind of residual connection, this is called as residual connection, having just one more route for previous signal, okay? In ResNet, this is the VGG19, having 19 convolutional layers here. And you can simply extend it to have the 34 layers, but this will not be better than this VGG19 because of the vanishing gradient. But if you have this kind of residual unit in between the layers, thanks to the characteristic that I mentioned here, the gradient becomes more stable, and they are now works. Okay, and even thanks using this residual connection, their performance is actually becoming better than this VGG19, having less layers. Okay. And this is the implementation of ResNet. I will show you only the important part. When implementing this ResNet, most of the blocks are similarly defined as before. Okay, they are just, just the defining multiple convolutional layers. Okay, but here bottleneck unit is this one, implementing this one, bottleneck unit. Bottleneck unit, it have multiple convolutional layers. This is the original path, okay? This is the original path. Okay, but in the forward path, this part will calculate this, okay? And this part will add the original signal X, okay, to the calculated signal, okay? So the implementation of residual connection is also very simple in the PyTorch, okay? And you can, first, you can apply convolution value max pooling for the first layer and apply multiple bottleneck layers to implement the ResNet architecture. So this is the implementation of the ResNet, okay? Are you guys understanding this? Okay. Any questions? Maybe not. Okay. So this is the end of the lecture 3. So, next Monday, 3:30 or 31, I'm not sure. Next Monday, actually, we will have quiz 1. Okay. So you can bring paper materials. This is the open book exam. So you can print out lecture slides, maybe, but no electronic devices are available. Okay. So don't, give laptops. Okay. But you can print out your lecture slides. Okay. Or you can also write down something. Okay. And also, maybe it will take 1 hour, but it will be sufficient maybe, and there would be 2 to 3 problems in quiz 1. Okay. If you understand everything clearly, then it will not be difficult. Okay. Any questions? No? Then let's finish here. See you next Monday. Thank you.